Innovative four-state logic emulation for power-aware verification. Abstract. This paper introduces an innovative four-state logic 0, 1, X, or G. The simulation technology will illustrate its application to an actual mobile AP SoC for power-aware verification, marking a first in the verification industry. This four-state emulation is highly useful for identifying the power-intended bugs and simplify the debug of the X sources. The implement in emulation performance significantly enhanced the overall verification turnaround time. Additionally, this paper presents unknown X-value sources which are implemented in the emulator compared to the simulator and outlines the key requirement for a successful adoption of four-state build emulation. This paper also compares the research of the four-state emulation experiment with the traditional simulation-based verification and show how much faster it is than a four-state logic simulation. This paper shared the experimental data on the additional resources required for four-state logic emulation compared to two-state logic emulation. Introduction. Power-aware verification, including UPF, typically takes more execution time to standard logic verification. Therefore, to improve the power-aware verification turnaround time, the emulation could be a beneficial solution since it is faster than simulation and most emulator vendors support UPF. The power-aware simulation depends on the X propagation to display the effect of the power. Using this, the designer can identify bugs related to the missing isolation cell or any enable signals. For example, isolation enable, which is not active and could cause the isolation cell to malfunction. Furthermore, a significant debug issue in power-aware simulation is identifying the root cause of unknowns, X's, and values on various signals. There can be many reasons why the X values appear on signals in power-aware simulations, ranging from the incorrect UPF specification, missing isolation, level shifting retention cells, or improper power domain partitioning. However, traditional emulation methodology only supports two-state logic 0 and 1, so the X and Z values are not supported. Even in power-aware verification, with this limitation, we might overlook some power isolation issues in power-aware emulation because 0 or 1 value is propagated instead of an X when using two-state logic emulation. Sometimes this non-intuitive emulation method makes debugging more difficult compared with an RTL logic simulator. For these reasons, logic verification engineers use emulation only for power sequence checking, not for their power-aware verification. So the traditional emulator does not replace logic simulation in the power verification area, even though emulation could reduce their verification turnaround time. However, the size of the mobile and automotive SoC is increasing. The development period is getting shorter. Even the number of power domains is rising as chip architects incorporate the finer grain the controller into chips and the system, adding significantly to the complexity of the overall design and verification effort. Therefore, logic simulation is insufficient in this increasingly complex and challenging SoC verification situation. Chapter 2. Four-state logic emulation. In the light of this challenging SoC verification simulation situation, my team and emulator vendors have been discussing the development of the four-state logic emulation to improve the power-aware verification for the past 10 years. Finally, last year, four-state emulation became possible. This paper describes how the four-state logic emulation was developed and including the historical background. It shows the unknown X-value sources that are implemented in the emulator in comparison with the simulator. The emulation process with the flagship mobile SoC is introduced, along with some requirements for successful four-state logic emulation adoption drawn from our experiences. For result analysis, we share a runtime and compile time comparison with the logic simulation. Finally, a hardware resource comparison with the two-state logic emulation is shown based on the experimental data. The 4. Innovative four-state logic emulator. Hardware emulation has long been implemented with two-state logic, where the de facto standard for software-based simulation is four-state logic. The use of the two-state logic for emulation was an accepted trade-off for the performance gain and the emulation effort, and it was thought impractical to implement four-state logic in hardware. The increasing adoption of low-power design with the increasing size and complexity is challenging the accepted idea that two-state emulation is good enough. With a novel implementation of native three-state 0-1-X computation in a parallel Palladium Z2 processor along with additional compiler logic transformations to add Gibs support, so the four-state hardware emulation is now practical to implement and well suited for low-power verification. The introduction of X to develop low-power handling is the primary focus on this paper, but there are multiple possible sources for X in the emulation in the design. So the table 1 shows the source of the X from the simulation and how they are handled in four-state emulation with the Palladium Z2. Table 1. The four-state emulation and X handling. The usage of methodology for four-state emulation retained the same feature, the compile flow and the runtime operation as two-state emulation. And the same way LO emulation flows, four-state emulation operates on a synthesized representation of the design. The Palladium Z2 processor hardware introduced the ability for processors to work individually to emulate two-state operations, so in pairs of perform the logical equivalence functionality with four-state logic. Due to the usage of the processor pair, the emulation resources required for four-state calculation must be at least 2 times that of two-state calculations. B. Evaluation with mobile AP. This paper describes the evaluation journey and the issues we encountered during the evaluation period, then summarize the for successful four-state logic emulation adoption. Firstly, the capability of the four-state logic emulation with the various X situations were confirmed by checking the state corruption due to the UPF power down, so the X propagation and uninitialized signals through an example design. So figure 1 and figure 2 are snapshots from the four-state emulation waveforms. Figure 1 demonstrates the state corruption due to the UPF power domain and the X state for initial values until reset. The waveform accurately shows the unknown state, making it helpful for debugging power intention with the UPF. The figure 1 is state corruption due to UPF power down. The figure 2 displays X propagation for small counter logic. From the beginning, the first X value to count 3 and X values are propagated to the upper bits. Four-state emulation also supports X propagation situations. This feature will assist in finding the root cause of X through the valid waveform. Fear 2, the X propagation. The main evaluation with the full mobile AP SoC design was started. The target design has over 20 different power domains, and the target evaluation scenarios are system power gating cases. And based on the evaluation, the following requirements are needed for successful four-state logic emulation. 1. Power-aware synthesizable for emulation phi model. All power features should be implemented fully in the model, including power pins, and the model should be working with the UPF at the same level as the simulation model. In the most cases, 5 models for simulation have many fully featured power-aware models, but most of them are not synthesizable code, so they are not for emulation environment. For example, in the DRAM 5 model, there were issues with the DRAM access because all power features were not implemented exactly, and this occurred in a simulation system power gating scenario when the DRAM controller was powered off. After waking up from the system off, DRAM access was not possible, which was an issue caused by lack of retention handling in DRAM's reset. Okay, next is number 2, the power pad mix implementation for taking care of the high impedance and X values. For example, the bidirectional pad signals should be considered with G values in four-state emulation. The following I assignment RTL coding style is working properly in two-state emulation environment due to two-state emulation doesn't care high impedance, high G cases. But it might not work properly in four-state emulation, which supports the high G cases. It should be fixed to support high G cases, like the number 2, and I assign pad equal on the four-state equal is 1bx is a ternary operator as 1bxn colon pad underscore I semicolon might not working properly. And second one is there is consideration of the PG one PG, and if it is synthesized correctly. The next is the number 3. It's the removal of dynamic RTL emulation debug feature. Dynamic RTL is one of the debug features in emulation. Dynamic RTL model is included in the static compile time, but it can be added to just before the runtime. So it is useful to implement debugging modules without additional compilation time, but dynamic RTL is not supported with four-state emulation. So any monitor or debugging logic which is implemented with dynamic RTL needs to move to a static RTL implementation. Number 4 is handling pull up and pull down for Z-state net. Number 5, initialization. Initialization is on driven nets in both test bench and on emulation model. 6 is SRAM ROM coding preloading. Preloading to avoid unexpected access propagation after accessing an uninitialized memory region. In a two-state emulation environment, emulation rarely stops because the memory output value is 1 or 1, even if the value is not initialized. However, in a four-state environment, if the memory is not initialized, the memory output value X appears in the memory output value X appears, and this value is propagated, making debugging very difficult. And C, result. The result shows how much faster The four-state logic emulation is then logic simulation in terms of performance, and also how much more accurate it is than the existing two-state logic emulation in terms of power-aware verification with full support for hardware power-aware features using UPF. Firstly, let's look at it from the performance perspective. Figure 3 shows the runtime and compile time comparison of two different SoC designs, Design A and Design B. The emulation compile for Design A is 16% more than simulator, but the runtime performance is improved by 115 times. The Design B is a larger chip and target power scenario is more complicated and longer than that of Design A. The compile time gap is wider, but the runtime gain is smaller than Design A. This result appears to be due to the physical factor such as hardware emulator resources and emulator driver clock frequency. In the full chip SoC power-aware simulation, most power scenarios take over 1 or 2 days of simulation time, one clock. However, this innovative four-state logic emulation allows for a result 30 to 115 times faster than the simulation, depending on the size of the test scenario. Regarding compilation time, the emulator compilation has traditionally taken longer than a simulation because the hardware-based emulator requires design synthesis to run. Thus, the compilation time takes 1.16 to 1.7 times longer than that of the simulator. Since each power scenario typically runs more than 10 times to complete verification, this performance improvement significantly help enhance the overall verification turnaround time. Figure 3 is run-end compilation time. In terms of the accuracy of the power-aware verification, this paper shared two experiences. First, there was an issue with an X occurring after power down in a ROM that always needs to be powered on, which was actually caused by missing Liberty cell for the ROM, which did not properly reflect PG pin information and was connected to wrong power supply net, causing the power to actually go down and the ROM 2 failed to keep data, resulting in an X appearing at the ROM's output and propagating. And another one is the other is the power switch control signal seen as X in corrupt power domain. In this case, the tool interpreted the wrong interpretation of set underscore power port underscore attribute, the minus driver underscore supply or minus receiver underscore supply script in the UPF, leading to the power switch signal being treated as X. Both of these phenomena did not occur in two-state emulation. The resource analysis. In this section, this paper presented experimental data on the additional resources required for state logic emulation compared to state logic emulation, and primary factor we tracked are compiled capacity, compile time, and performance. Table 2 employs the ratio relative to the base 2 state without UPF configuration to clearly illustrate the impact. Emulation capacity refers to the volume of resources utilized by the emulator hardware. Four-state emulation requires approximately 2.3 times more resources than two-state emulation. Adding UPF increases the overall resource usage by approximately 3.2 times compared to the default configuration. However, this is only 2.3 times compared to a two-state UPF configuration. The extra resources needed, along with the traditional processing of UPF construct, resulting in an extended compile time. The initial emulation speed is influenced by both addition to the UPF and the introduction of four-state logic. Table 2, Resource Analysis. The result of this experimental represents initial data without any optimization applied. Precise profiling for capacity and compile time and performance will be planned to optimize each factor. It may be beneficial to use a hybrid form from where the verification target block is set to 4-state and the remaining blocks are set to 2-state. In addition, further work will include checking waveform dump time and convince time, and both essential debugging and the experiment. Traditionally, it takes a long time to dump the waveform in the emulation and convert it into the format used in the debugging, which is presented in a hurdle in a debugging turnaround time. By selecting useful features related to this waveform, not only in a 4-state environment, but also in 2-state environment, we should be able to shorten all the overall verification time. Chapter 3, Conclusion and Future Work. This paper introduced the innovative 4-state logic emulation technology for power-aware verification and presented the evaluation result through an actual mobile AP SoC project for the first time in the verification industry. The 4-state emulation is highly useful for identifying the power intention bugs such as missing isolation cells and make it simplify the debugging of the X sources. This paper demonstrates which X sources are implemented in 4-state emulation, which is almost equivalent to 4-state logic simulation. Therefore, most power scenarios can be run in this 4-state emulation environment, and verification turnaround time will be significantly improved. The drawing from the evaluation experience in this paper presents the key requirement for the successful adoption of the 4-state emulation. Most of the requirements for resolve around the full-feature power-aware models for emulation that takes into account the X and G of the phi and pad models. Additionally, care must be taken with undriven nets, pull-up and pull-down handling, and the memory initialization. The experimental result level for state emulation is significantly faster than the simulation, approximately 30 to 115 times faster, depending on the size and the scenario complexity. So this resource analysis can be beneficial to anyone planning to adopt the 4-state emulation methodology. This paper has so far focused on implementing 4-state logic emulation environment and low-power verification. Therefore, in this experiment, compilation time and performance analysis have not been conducted. As this paper shows the resource analysis section, one experimental data for compilation time and performance are shared after load. The detailed profiling for each resource item will be planned, and that optimization approach will be properly applied to improve the compilation and performance. For further work, and an in-depth analysis of the debugging features for a power intent, including waveform, will be likely be necessary. to provide an environment mostly identical to the one verification engineers previously used in the simulation environment, so the various convenience features must be supported. Okay, anything? Okay, acknowledgement. We would like to express our appreciation to our team members who assisted with the debugging, especially in finding the absolute causes, and to 5 modeling team who implemented synthesizable emulation 5 models. And also we would like to thank the Cadence members who collaborated to enable this methodology. Thank you for your time for this paper. This paper is the DVCON2024. It's an innovative 4-state logic emulation for power-aware verification. Thank you for your time again, and see you next time.